The universe is full of wonders. It has sparkling nebulae where stars are born, it has planets of ice and gas giants, and it has some of the most mysterious objects we have ever imagined. Black holes. What are they? Imagine a star much bigger than our sun reaching the end of its life. It runs out of fuel. It can no longer hold itself up against its own immense gravity. The star collapses inward, crushing itself into an impossibly small point. It creates a place where gravity is so strong that nothing, not even light, can escape. That, in essence, is a black hole, a one-way door in the universe. They bend the very fabric of reality around them, invisible, yet we know they are there from how nearby stars dance. Black holes are the universe's best-kept secrets, challenging our understanding of physics, of space, and of time itself. We are not just looking at stars and galaxies, we are also looking at the shadows they cast. Black holes are those shadows, engines that power galaxies, and ultimate cosmic puzzle boxes. Imagine you are an astronaut floating in your resilient spaceship, the ship of the imagination. Your destination is one of these cosmic monsters. From far away you can't see it directly, but you can see its influence. The black hole acts like a giant lens in space, gravitational lensing, warping light and revealing where gravity is king. As you get closer, it reveals a perfect circle of absolute blackness, its shadow. Around the edge glows a thin, brilliant ring of light. It's made of photons, particles of light trapped in orbit, some circling for a very long time before reaching your eyes. A beautiful yet terrifying halo, the boundary of the abyss. Now you feel the first physical effects. The side closer to the black hole is pulled more strongly than the side farther away. A tidal force, like Earth's ocean tides, amplified to an incredible degree. Space becomes a powerful river pulling everything toward the center, a cosmic waterfall, and you are the canoe nearing the edge. Ahead, starlight blue shifts to higher energies, behind it red shifts and dims, the universe changing colors as you enter a dangerous realm. You reach the most famous part, the event horizon, not a wall but the point of no return. Beyond this line, escaping would require speeds faster than light. Impossible. Crossing might feel surprisingly gentle, especially for a supermassive black hole. Outside you could go forward, backward, left, or right. Inside, all directions point to one place, the center. Space-time itself falls inward faster than light. You are caught in its current. Like rapids you cannot swim against, like running up a downward escalator moving faster than you can. Rockets roar, but you still go down. Inside the horizon, all possible paths through space-time end at the center. The future narrows to a single destination. You have made a one-way trip. From this moment on, your destiny is sealed. As you continue past the event horizon, that gentle stretching intensifies. The difference in gravity between your head and your feet rises alarmingly. Your body and your ship are pulled longer and squeezed thinner, a grisly process called spaghettification. First an uncomfortable pull, then unbearable strain. Bones snap, tissues tear. Every atom aligns into a thin stream, heating as it is stretched and compressed. Fall into a small black hole, and spaghettification starts before the horizon. In a supermassive one you cross intact. The stretching comes much closer to the center. The plunge from horizon to center is swift, a force that crushes everything. Before the very center, even the atoms that were once you fragment into fundamental particles. It is the raw, unforgiving reality of physics in an extreme environment. One of the most mind-bending parts is time. Gravity curves not just space, but also time. The stronger the gravity, the slower time passes. This isn't science fiction, it's measured. GPS satellites must account for it. For you falling in, time feels normal. Your watch ticks steadily, your music lasts its usual minutes. But to someone watching from far away, your reality diverges from theirs. Approaching the horizon, your clock appears to slow. You move in slow motion, approaching an infinite delay. You seem to freeze at the edge, reddening and fading, never quite crossing in their frame. So who is right? Relativity says both. Reality depends on your frame. Inside, the singularity isn't a place you can see. It's a moment in time. It is your future. No matter where you look, your future ends there. Like walls closing in from all directions. Extreme warping compresses the entire outside cosmos into a small, bright window. You might watch the universe's future race by in fast forward. Direction breaks down. The singularity, the end of your time, is everywhere. Even light from your dashboard cannot travel away. The front of your ship becomes blind to the back. In a sense, space and time swap roles. inward becomes as unavoidable as time's marches to us. In these final moments before spaghettification erases you, you're in a unique pocket of reality. Your personal timeline about to be extinguished. Let's rewind. Change our perspective. This time, you are the observer. As your friend's ship approaches the black hole, their radio signals stretch to longer wavelengths. Voices deepen, slow, and slip beyond your receiver. On your scope, their clock runs slower. The ship seems to decelerate, never quite reaching the edge. The light shifts from white to yellow, orange, red, then beyond visible to infrared microwaves radio, and fades to black. To you, they are forever suspended on the brink. To them, the end comes swiftly. Both are real in their own frames. What lies at the singularity? Our equations say, all the mass crushed into zero volume, infinite density, gravity and space-time curvature blowing up. That nonsense signals a limit of our theory. General relativity excels, until the center. There, we need new physics. We seek a theory uniting the very large with the very small. Quantum gravity. Maybe quantum effects halt collapse, a finite ultra-dense core, a Planck star. Or wilder, a gateway, even a newborn universe. We don't yet know. Black holes test nature's laws. LIGO heard ripples from colliding black holes. The Event Horizon Telescope imaged a black hole's shadow. Stephen Hawking showed they're not entirely black. Quantum effects let them radiate and over unimaginable times evaporate. By studying them we ask, what is space-time? How does gravity work at the smallest scales? Where did the universe come from, and where is it going? This is a golden age. Each waveform, each image pushes the frontier. The story is far from over. The universe is stranger and more wonderful than we can imagine, and the exploration has only just begun.